All right, let's come to the last section of Chapter 4. This is Section 4.8 about linear approximations and differentials. So in this section, we're going to learn about something which is used in math applications called linearization, which leads to the idea of a linear approximation. And then we're going to connect that idea to this other idea of differentials, which can be viewed as like a way of talking about linear approximation. But it's also important for calculus more in general. And then the topic of differentials is going to be something we need to sort of put out there and discuss to help us move towards talking about integrals, which will be the main topic of Chapter 5, our last unit for the semester. So first of all, let's talk about linearization. If you've got a function, here's a function, say this is f of x. If you've got a function and you're applying this function, you're doing some application, perhaps you only care about x values in a particular range. So let's say you really only care about x values in like this range right here. Okay, everything outside of this range, like you don't care about. It's not relevant to your application. You just care about this. Well, what you can do is pick a number sort of in the middle of that range. We're going to call that c. Look at the point on the function right there, and then find the equation of a tangent line. Let me grab my ruler here. Oh gosh, there we go. Let's find the equation of a tangent line, a line tangent to this function at that point. There we go. So near that point on the graph, this tangent line and the actual function itself are really close to one another. So if we kind of go like this and just focus on what's in between these two lines here, on that segment of the function, the line and the curve are pretty darn close. Like they're very similar. The difference between them, the vertical difference between them, is small. It gets bigger the farther away you go. Like over here we have a pretty big difference between these two functions vertically, right? The outputs would be significantly different. And also, if you can imagine extending this out over here, potentially we have some really big difference in value between the functions, like the behavior of the line and the behavior of the curve could be radically different. But at least in this region over here, that's a pretty small difference. And so what we can do is we can approximate the function by its tangent line, and the tangent line is called L of x, and L of x is in this case the linearization of the function f of x at the point x equals c, whatever x value you chose as your point of tangency. Okay. So let's review how to find the equation of a tangent line, and that's therefore how to do a linearization at a point. What we're going to do is I'm going to write the equation of a tangent line, and I'm going to write it in the point slope form. So I'm going to write y minus the y coordinate of the point. Well, this point's coordinates here are going to be c comma f of c. Okay, because it's a point on the curve, which is the graph of f. So the y-coordinate is f of c. And then that's going to equal the slope of the line. Okay, so we're looking for an equation for the line, and its slope is given by the derivative of f. So that's f prime, evaluated at the point of tangency, which is c. So there's my slope, times x minus the x-coordinate, which is c. So there's the equation. So now all I have to do is just add this f of c to both sides. Okay, and then I get y equals that. That would be equation of the line. Now we're going to put that in terms of the function. The linearization would therefore be L of x equals this f of c that we added to both sides plus the slope f prime of c times x minus c. And that right there is literally just the equation of a tangent line, which we already learned. But we're going to use that here as our formula for linearization of a function f at a point c. So now from this idea of linearization, we then can do what's called linear approximation. And the linear approximation is to say, basically, that f of x is going to be approximately equal to L of x for x values near C. And what near means kind of depends on how accurate you need your approximation to be. So I'm going to show you in an example later how you can determine the sort of interval around C, which would be this interval here. How can you determine like the width of the interval around C that will ensure that your approximation you're doing is accurate to within a certain like maximum error that you're willing to accept. So that would be like saying how far out can we go if we want to keep this purple distance, right? This purple distance between the two functions. If we want to keep that distance small enough to within like a reasonable error, okay? So that's the idea. In the next video, I'm going to go over an example.